Okay, chapter one, introduction and mathematical concepts, or as I like to refer to it, building blocks, because these are the foundations that we will need for the rest of the semester. We hit on a bunch of different mathematical ideas here, some of which you may have seen before, some of which you may have not, in which case I encourage you to take extra effort to make sure that you do understand it. So, first off, let's take a look. What's the nature of physics? So physics is a subject that's developed out of the efforts of men and women to explain our physical environment, everything around us. It encompasses a ton of different phenomena: planetary orbits, radio and TV waves, magnetism, lasers, so much more. It's just about limitless. Everything around you, which is so cool. And I hope that this semester you'll start to see that too in your everyday life, or when you see news articles, you'll be like, hey, look, that's physics. So that's where we're headed. What physics tries to do is it tries to predict how nature will behave in one situation based on the results of an experimental data that was obtained in another situation. So Newton developed these laws of motion, and from that we can predict what happens with rockets when we launch them into space. Maxwell came up with a set of equations that you'll learn about if you take physics 2B. And from that, we have telecommunications, right? We have cell phones and all sorts of other devices. Out of one scenario, we learn something entirely different. So sometimes physics seems a little bit abstract and theoretical, but it's because we're learning the things that can be applied to a variety of situations. Right, section 1.2 takes a look at units, and units are so crucial to physics. They pop up all the time, and really units are one of your best friends because if you keep using them consistently, they'll always have your back. So that's just a little intro, but what are they? Well, physics experiments involve the measurement of a variety of quantities, right? You might measure length or the weight of something or how much time something takes. These measurements need to be accurate and reproducible. You don't want to measure something to be one length and then the next day you go back and you're like, oh, it's a different length, or someone else comes to measure that same table and they find a different length entirely. That'd be kind of concerning. So the first step in ensuring accuracy and reproducibility are defining the units in which the measurements are made. So units have standards that they're tied to. So SI units are something that we'll be using. It's the scientific method, or the metric system is another term that's often used with this. And we'll see within SI units that we have the meter, which is abbreviated as M, is our unit of length. The kilogram, abbreviated with kg, is our unit of mass, and the second is our base unit of time. And these all had set standards at one point. So here is shown two different people holding the original meter stick. The definition of what 1 meter is was they developed a rod, very fancy rod, but they said, this is exactly 1 meter, and we can make very precise copies and send them around the world, and that way everyone will know what 1 meter is. Since then, we've gotten it to be even more accurate by defining it in terms of the speed of light, which is cool. Similarly for mass, there is a literal chunk of metal that's exactly 1 kilogram. And that's why mass has a unit that's not a gram. It's the only one that has this extra kilo prefix in front of it, because a single gram would be tiny. It'd be really hard to have a consistent standard based on that. So they use a full kilogram so that it's a sizable chunk that can be maintain the accuracy. And here you see it has these 2 jars on top of it because it's held under vacuum to try to keep it exactly that mass. But even that has slight errors over time. And so the mass actually was recently redefined in terms of physical constant, Planck's constant. It's an interesting tidbit. And perhaps most familiar to us, because it's the same in the imperial or American system, is the second is our unit of time. So what you have going by on your stopwatch is a second, and that's usually defined, it was originally defined in terms of like hours in a day, right? Rotations of the Earth around the sun versus the sun. Now it's based upon atomic clocks. So the key here is just knowing the meter, kilogram, and second. Those are our standard units that we will always want to get back to. So if you have something in centimeters, you're probably going to want to write it in terms of meters. So the units for length, mass, and time, as well as a few others that we'll get to later on, are regarded as base SI units. That we can use basically these 3 units, length, mass, time, in combination to define additional units for the rest of the semester. So we'll be able to combine the units to define force, to define energy. We'll mash those units together and we'll get a new unit called joule, my favorite unit. But it just goes back to kilograms, meters, and seconds. So mass, length, and time. So yeah, those are our standards. And here's a nice comparison, units of measurement with different systems. So the SI is the one that we're going to be using here, as mentioned. So that's the one you have to focus on. But CGS is another one that sometimes pops up. It's based on the centimeter, the gram, and the second. CGS, cool. And then the British system, or imperial system, which is often what's used here in the United States, is the foot for length, the slug for mass, which is similar to the pound, but pound is technically weight, not mass, and then the second for time. So at least time is consistent in terms of units here. Now, why do we care about units? I mean, and there's all these weird names for them. What does it really matter? Can we just let them go? Well, it turns out not so much. And I have some examples to highlight that. So here's one, Mars probe lost due to simple math error. This was back in 1999. NASA lost its 125 million Mars climate orbiter because spacecraft engineers failed to convert from English to metric measurements when exchanging vital data before the craft was launched. So the NASA team at JPL uses the metric system. Lockheed Martin, which is a huge engineering firm, used the American or English units, right? And they provided, one of the teams provided the acceleration data, and they didn't write the units there. And so the other team said, oh, acceleration, this is obviously the metric units or the English units, but it wasn't. So because the units weren't explicitly written out, they got the wrong number. And the Mars probe was totally lost. In a sense, the spacecraft is lost in translation. That is so dumb. So this happens at the highest level that people make unit mistakes, and it's why I encourage you to be really thorough in writing your units out. Now, maybe you don't relate to engineers so much, maybe you're not interested in that, that's totally fair. So here's an example that's not engineering. Northeast students almost died after taking equivalent 300 cups of coffee in one dose when experiment went wrong. So this is more in the medical field, right? They're trying to do a study on how caffeine affects individuals, and they made this routine maths mistake. There's 100 times the dosage that should have been given. They put the decimal point in the wrong place. They were given basically 30 grams of caffeine instead of 300 milligrams. So the units there made a huge difference. So please pay close attention to your units. Fortunately, in this case, the people survived. They had violent side effects and spent days in intensive care, but they didn't die here. But down the road, there could be people's lives at stake under your care. You're responsible for them, so make sure that you know how to do these math errors right. You know, it's like, oh, well, what's a decimal point between friends? It's almost the same, and it's 100 times the dose of caffeine and can nearly kill someone. So people's lives are at stake. So this is the time to practice while it's low stake, while people's lives aren't at stake, just your grade, and make sure you can get it right. So that's an introduction to units. In the next video, we'll take a look at how we can use units in problem solving. So stay tuned.